Welcome to our IT Academy Research Summit. My name is Jaak Vilo. I've been from Tartu University side responsible for this research program in here. And we have packaged into 2 days full scope of what we have been up to over the last 3.5 years or so. My role is only to give a little bit of background, what is IT Academy, why the research program, and then we will turn to the actual content about AI, big data, robotics, IoT topics. And these all researchers whom we are going to see are working at the University of Tartu. They have been recruited on this IT Academy research funding mechanism at the Institute of Computer Science, where we are at the moment, plus Institute of Technology that is in the Maaremoisa campus, but partly also in here. Okay, please can I get my slides? Excellent. So on the right, there is a document, historic document from, I think, 2009, when Estonian Development Fund approached Parliament with a document of agreement where universities, IT companies, Union, ITL, and Estonian Development Fund together said that we need to do something to increase the IT education. That coincided, it was known that after 1990, population decline happened in Estonia, birth rates dropped by 45%, and that wave was about to come to universities. So everybody was in shock. What will happen? We need more IT people, but the population disappears. So that was the background, and the letter signed by rectors and ITL basically said that universities should do something about IT education. Our institute said back then, Tiit Roosma and everybody else, we read that from the newspapers. That was good news, but that's how it was. 2011, the first program was started, and ICT program using structural funds to help the education side. That was renewed 2016 on the education to support some curricula, actually 6 curricula in Estonia. And 2019 to this summer, there has been this IT Academy research program with the goal to increase the capacity at universities, the number of people, and also the topical aspects of that. I'm coming back to that. At the moment, we are heading to the very end of this current program, and the new program is in the making. It's in the boiling phase, lots of emotions about the new program, and we want to also help to convince that this current program has had tremendous impact, and these kind of activities should be continued in Estonia. A little bit of numbers. These are from University Statistics Dashboard, number of students at the Institute of Computer Science. As you can see, this is instead of population decline, we have basically tripled the number of students studying in here at Tartu in the IT subjects. And already when we started this growth, we were understaffed. So the student to teaching staff ratios were awfully bad, about 25 or 30 to 1 teaching staff, and we have tripled in the number of students. So we have had to keep pace with this growth. So this current research program really aims to do 3 things. To help the teaching needs on the education side, hire more staff to teach students, to supervise student research topics, bachelor's, master's, PhD education, and increase industry collaborations. Increase the opportunities for industrial collaborations. by bringing in topics that are most needed by the local companies in here in Estonia. So that's why there is this topical aspect of focus on AI, big data, robotics. Overall in Estonia, the program is about 3.4 million euros per year. There is also Taltech and Tallinn University involved. Tartu University's share is 1.35 million per year, and out of the 7 areas, 3 are the responsibilities of Tartu University. I have mentioned that we have 3 topical thematic areas. So we have also 3 scientific advisory boards to assess the programs, help researchers in their research, and also to offer sort of like their insights how to increase the collaborations between the groups or towards the industry. We knew that we will have that funding, and what we did as a strategic choice was not to go after 3 top professors and try to attract them to Estonia, because we somehow felt that this is not going to happen. No big professor will leave their job and move to the other country too easily, right? So our focus was to really go for more principal investigators, PIs, more groups, more research groups, mostly younger, earlier stage researchers who get the opportunity to establish their groups. So to build on the new growth, really. And also topically, we were not very selective, but we wanted to kind of see that it fits with our teaching needs and supervision needs. Added benefit today, it's so popular to talk about sustainability, is that when we have more variability, more diversity, this is good for sustainability. So more smaller groups would be better in that sense. And therefore, this is an excellent starting opportunity for groups, and we will see what they have been doing so far. I did mention the growth. I put on the same scale the number of students. This is the dashed line total, but split in master students, PhD students in green, and bachelor students. So the biggest increase has been in masters, and the blue line with the dots is staff members. So around 2019-20, you can see that actually we have managed to increase a little bit faster the number of teaching academic staff compared to the student numbers. And the same ratio of all academic students to all the academic staff over the years is in here. After the change of the career path, there is no separate teaching and research tracks anymore, so now they have been merged together, but half of the academic staff have been funded from the research funds. So you can see again from 2019-20, we have managed to improve this ratio. So less students per academic staff members. Subtracted here are PhD students who would be junior research fellows mostly. Therefore, we are coming closer to the topic of today. We have these 3 thematic areas: artificial intelligence and machine learning. Initially, it was meant only for health, but actually we have, it was turned into much broader. So it's not only about health and biology, but broader. Second, the data science, big data, and security aspects, and robot-human collaborations, Internet of Things in industrial processes. In those areas, we have advisory boards. We have 3 advisory boards, and these are the names of the people who are there. The demand was definitely to have international members, members from Estonian companies, members from public sector, and also members from the other universities. So it's a composition of international companies, public sector, and universities. Not everybody is in here today, but tomorrow we will have a closed session where we will discuss also with the other members in there. Just in case, do I dare to ask, please raise hands who are in here present from advisory board. There are some, and about 5, 6 in here. We used to have 3 different events every year, and now it was supposed to be twice a year, but running 6 meetings would be a little bit too much, and this time we are approaching the end of the program, so we thought that it would be better to bring everybody together to see the full impact. And besides the advisory board members, there are observers. Harno is through which entity we get the funding, and the IT companies League, Torispöld, Martots from there. Of course, people over the years have been changing jobs, so maybe some of the job titles are not entirely correct anymore, but this was set from the beginning. And now 2019, we started with the recruitments, first recruitments, managed to get 2 people PI started 2019. 2020, we already had 14, 15, 18. There have been also a little bit of churn, so the numbers are, that's why they are not perhaps so precise, but I think today we have 16 groups. It depends how we count the groups exactly. But you can see also the numbers, that how these people and their groups, they started to hire PhD students, master students, how their productivity went up. So number of publications is now exceeding 100. With a small caveat, there might be some double counting, because one year you report that submitted, the other year accepted and published. Or there is a little bit of that double counting, but my gut feeling is about maybe 15–20%, not much more. But still, you see that it takes 3–4 years to get the groups up and running at full speed. And in total, in a joint Excel, I was just counting number of people whom they are supervising, bachelor students, master students, PhD students. That this accounts in total over 150 people being supervised in those groups. So this is a massive amount of people, and for the Institute, it accounts for about 1/3 of the entire Institute. So it has been very significant for our university. And university is doing well in computer science rankings. We have been rising, now in top 200, around 200 worldwide by Times Higher Education. On the left, there are some measures. We can still see that on the research and teaching, that are 2 lower bars, we are not doing that excellent yet. So there is a room of improvement also on that side. But thanks to these groups and their ambition, I think we will be doing great over the next years as well. So IT Academy Research Summit in a nutshell, these 2 days. We have only 2 plenary sessions. We have selected a small number of presentations that you will hear over these 2 plenaries. The main event is about networking, and on the second floor we have long gallery full of posters. So the poster session where all the research groups and their members are present, so you can approach individually, see what they are up to, and have one-on-one these in-person contacts, the networking. I counted there were about 50 posters. So again, the scale of this event. On top of that, for tomorrow morning, we have also speed dating ahead. So the people from the companies, representing the companies, you can select with whom you would like to have one-to-one meetings, so 15-minute slots allocated, and you can book them. I will show you soon the QR code to the link, so grab your phones, be ready. We will close the meeting with an advisory board meeting, from whom I'm asking feedback on the program in total, and maybe some comments about good and bad aspects, and perhaps recommendations for Estonian government as well. But the entire meeting is really about networking. That's why we have this in physical presence in here, poster sessions, dinner, free mode, networking, and also these speed dating events. I promised you poster sessions. That's what it looked like yesterday evening and this morning. So there are, everybody is waiting. Please approach them. And speed dating, here is the QR code. It's from the event website. There is also a link, so you can select with whom you would like to have this longer in-person contact. After me now, I'm a bit, I have 2 more minutes. Jaan Aru, was Jaan present even? You didn't grab the name tag, that's why. Jaan Aru, Flores, Raivo, Kolde, and Arnis Paršovs will present. After that, we will have a coffee break and poster session plus reception and dinner. So after this session, all is going to be networking and fun. And tomorrow, we start again with a plenary, 9:15. Arun Singh, Edward Sevchenko, Naved Mohammed will present from our side. Mart Toots, who has been involved with us in this program, gives his reflections. Dan Bogdanov, one of the members of the advisory board, gives his. And also Peter Nurmi is present, will also give his viewpoints. I'm very excited to find out what they're about to say in there. So after this, the coffee break, speed dating, lunch, we still have posters, demos up, so as long as there is interest, it's going. And in parallel, we will have this joint SAB meeting. The final event will be closed session with the advisory board and the PIs and involved people from the different funders, etc. So ITL. So for most people, tomorrow after lunch, you can have still look at the posters, but we will have from lunch to lunch pretty much most of the event in here. And as you can see, next is going to be these talks. Everybody get ready to present in this order, and then we will have the coffee break. Thank you very much, and let's give the big applause to all the PIs who have been doing all the research and preparatory work. But also I would like to thank in advance the team who has been on the background setting up the event. So there has been a lot of organization going on. So nothing comes easy, so there have been people contributing, including the technical team ready to take the video. It's not streamed online, but we will have the recordings afterwards. So physical meeting, physical networking, that's what this event is about. Okay, is there any... Does anybody want to have any significant question? No, I thought so. So let's give a hand, give it over to the researchers, because this is their event, their spotlight.
Thank you. It's a pleasure to be here. And first of all, of course, a big thank to the IT Academy, because this funding allowed me actually to come back to Estonia and establish my research here and actually recruit many of these brilliant people, postdocs and PhD students. And I think over these 2.5 years, we have been actually fairly successful in the research. But today I was asked to present more like a vision of what's next or what could we do given this group and given this research. And I would like to say that this vision I would like to present, it only really captures, let's say, 1/3 or 1/4 of the research we are doing in our group. So before I go to that vision, I wanted to just give this brief overview that, the topic we are working on in our group is the question of basically what are the similarities and the differences between AI, artificial intelligence, and NI, or natural intelligence, our brains, right? There is internationally a growing community who studies these questions, tries to understand what are these points of where they diverge and where they converge. But this whole topic really became quite hot now since the last November when ChatGPT was released. Because, I assume everybody here has played around with ChatGPT. But the question is, when you interact with these kinds of systems, well, it gives answers as if it would be a human. Sometimes stupid answers, but humans also give sometimes stupid answers. So does it understand what I'm asking? Does it understand what I really want? How should we even answer that question? The whole topic and these kinds of tools then put on the spotlight this question of what are the differences and similarities between our brains and these AI systems. So that is one of the key things we try to figure out in the lab with all these people. But today, for the vision, I wanted to focus actually on one aspect of these GPT-like systems. And for that, I actually think that we should use this acronym GPT in a different way. And we should think of GPT not as a generative pre-trained transformer, but as a general personal tutor. And this has been known actually since the 1980s that if a person, any student, has a personal tutor, so someone who personally takes that student and corrects the mistakes, gives advice on how to continue learning, then these students will have massive increases in their ability to learn. And of course, when it was figured out in the 1980s, then these technologies were not there to actually do that. But now, in principle, we have these technologies. If you have chatted with these systems about a topic where you don't know, so on a topic where you are not the expert, and you want to learn, then you have probably felt that you can actually learn something, or in many cases, a lot from this system. So, in short, if these systems are used the right way, then they could be used as a general personal tutor for every student. And as you can imagine, this would be a revolution or a disruption of how education is given and how the education system works. And hence, the vision we are proposing or thinking of really doing, if we get the funds for that, is of a center that would be fully committed to studying these kinds of systems, their potential, developing new tools, and actually changing the education system for the better. And I will describe you this vision a bit. So the key issue for me is, and this is something I learned here thanks to the funding of IT Academy, that we cannot and we shouldn't be doing research, especially when it's about education, only in this ivory tower of research. But rather, we need to involve all of the stakeholders. And in our case, this approach is called a living lab, which means that you're not doing this the way usually research is done, that you are detached from the other players in the field, but rather you try to involve everyone from the get-go. So who are the stakeholders? I think some of them are those, all the stakeholders, but let's go through them. So first, essential component really when we talk about education is students, right? And the trouble with students and ChatGPT-like systems is that students, when left on their own, they don't figure out the best ways how to use these systems. They don't use these systems as a general personal tutor, right? Again, I'm not so much talking about university students. Everyone here who is a student, you are brilliant, you will know how to use these systems, I assume. But if we go to the pupils, so people who are in the 7th grade, their task, what they want to accomplish is to get the homework done as easily as possible. They will use it, or in fact, they are using it. As my sample says, I've been talking to students over the last months about it. So we want to include students in this project, and we want to develop these tools together with them so that we can quickly test some ideas and we can quickly bring knowledge to them, for example, about how to use this system so that they would be actually like tutors, so that they would actually bring about these massive increases in the abilities of the students. So we cannot wait 3 or 4 years in a research lab figuring these things out. We need to open this up to students. Perhaps it's even worse with teachers, because students already have used these tools. But when I'm talking to teachers, then most teachers kind of know that something like that, GTP, GPT, something like that is existing, but they are not aware of what it actually can do. So it creates this asymmetry where students are doing homework with these tools, and teachers are evaluating the homeworks as if they would be homeworks done by students or pupils, right? So part of this project would be also in really bringing teachers up to date and keeping them up to date with these developments. Again, we should not be and we cannot be detached from what teachers do and what teachers know. We need to bring this knowledge to them right away. Further stakeholders are, of course, edtech companies. And if you look at tools that are used for personalization in the wide world, then often these tools, they come somehow from a scientific background, but then very quickly, as you can imagine, commercial interests take over. And these tools quite often are not really up to date with what we should do to enhance students or what we should do to enhance teachers, but rather in making money. In Estonia, my experience tells me that my experience with edtech companies tells me that it's a bit better. The Estonian edtech companies are very oriented towards research. They want to know actually what we are doing. They want to know what the latest research is. They want to include us in the research projects. So I think there's a lot of hope there. But again, part of this living lab would be that these stakeholders would work together towards the same goal. And of course, we have to have the government on board. We have to have people from the government who agree that, yes, we have to fund these kinds of initiatives and we need to set policies that actually help teachers and help students, right? And this has been happening again in Estonia. When ChatGPT came, then the Ministry of Education and Science quite quickly tried to put together some guidelines, and they are, again, always asking questions from us. So these are kind of stakeholders that actually usually are not part of a research lab. And that's why I'm really saying that the vision is different from having a research lab. It's about including all of these players. Of course, there would be researchers there, but the key would also that we would like to make this actually open for international researchers, that if it's possible, we could try to create data sharing platforms and infrastructure for members or from other countries actually to be included in this and to take part in the data we have and join our efforts. Okay, let me skip that and go to the main goal, which is, of course, to use these tools to generate new and better ways for doing learning, to create tools that would enhance students and teachers. Again, although this might sound trivial, it is not, because of the problem, as I described, that the standard way of how students use it is actually, let's call it, not optimal, right? Not optimal for advancing their own knowledge and skills. So it's not only about AI tools that need to be generated, but more about also this background context of knowledge and skills we need to give to the students of how to use it. Or, in the best case, of course, the tools would be kind of self-explanatory. Again, the ChatGPT, for us it is. If you're a professor or a PhD student or a smart person, you can use it. But for a student, it's not self-explanatory how to use it the right way so that you as a student, as a person, would actually benefit from it, right? But to get to these new tools and to these new methods, what is needed and what has been kind of holding back the progress in the whole field is that one needs these very large-scale studies. So usually when, for example, researchers study personalized learning, then they do it in groups of tens or hundreds of students, right? But here, I think what is needed is actually that we try to do it nationwide. And that's why I do think that we need this kind of a center here in Estonia, because we have all the infrastructure already in schools to basically do this kind of nationwide study. And there have been people who have tried to do some of it, not with ChatGPT-like systems, but some kind of nationwide studies. But we could actually take it further and really, given this kind of living lab, do it as a study that incorporates the necessary control groups, etc., but does it almost in a nationwide manner. But before we ever get to that, I don't know if we will ever get to that because we don't have funding, right? Then what we can do and what we are slowly starting already now is to do these small-scale studies. This is usual science in the way that you do some kind of a small study trying to figure out some aspect, for example, of how this GPT-like system should be used in schools. But even these small-scale pilots you could do in this living lab manner, right? That you involve the students, you involve the teachers from the get-go. And as said, I feel that this is something that we are in a good position to actually do here in Estonia. And, when you look at this massive figure, then you might think, oh, this is just a big dream of an extremely short guy, right? But what I want to tell you is that when I was looking at it, then I realized that, yeah, it's a dream. However, in fact, we are already doing that. We are doing that. Just this morning, before giving this talk here, I was in a school in Tartu, talking to students. I was talking about how to use their brain and how to use ChatGPT for learning. Just last week, I was talking to teachers. I was talking to them, explaining them what are the capabilities of ChatGPT-like systems, what they can do. Last month, we had a meeting with EdTech companies in Estonia. And again, this is something, it wasn't obligatory or mandatory for these edtech companies to come and listen to scientists, but they came. Most of the Estonian big edtech companies were there. We discussed these issues. And in Estonia, the beautiful thing is that we are even, it's very easy to be in contact with the government. And in this case, for example, just this week, we had a meeting where we discussed personalized learning and where we discussed these opportunities. So in fact, we are already doing it on the small scale, and we will continue doing that, starting these smaller pilots, hopefully soon, and trying to take it from there. So I think it's a vision, it's a plan, but we will do it as good as we can anyhow, because really, as a researcher who is studying both natural intelligence and artificial intelligence, I don't really have a choice. I mean, I have to do this. This is the big topic that is in front of us. We need to study it and do our best, actually, not to simply study it, but as I explained here, involve all the stakeholders. This is an issue that's much bigger than research. This is an issue that involves the whole society, and therefore we need to take care of it. And thus, in the end, looking at this and trying to now find European funding, for example, for this project, I'm extremely grateful again for having this chance to have had the funding from IT Academy, which has helped me to actually even get to this position where I can dream big. Thank you.
We have microphones and can ask questions. Where are the microphones?
In the back.
They don't need to be significant questions.
Hi.
Hey.
Okay. So, question, societal aspects. I believe you have looked at those as well. So there is, if we're talking about population-wide, then I would argue, and you'll tell me where I'm wrong here, that this sort of a general personal tutor has an amplification effect. When Tony Stark invented the time machine, then it was the smart prompt that got his AI to give him the quantum thing, right? So you have to come to this general personal tutor with some pre-existing intelligence, and it will amplify yours. True or false?
Yes, I agree. I agree completely. So, and I tried to even, probably I did it very in a bad way, but I tried to emphasize it, that this is the thing that we need, why we need to include the students right now. Because the standard way how students do it is the wrong way, and then there's nothing to amplify. So I completely agree, and that's why I think that, you know, this is a very timely matter that we need to even sort out in some sense before the next school year starts. Because, again, my experience tells me students are using it, and they use it exactly the way you expect them to. They do their homework with it. Right? But we want them to understand, and this is one of the hard parts that cannot be solved simply by technology. We want them to understand that they have to be the ones who ask the questions, they are the ones who are the agents, and then, and only then, this general personal tutor can help and, as you say, amplify them. Right? So this is the general knowledge we have to get across basically to the whole society.
Okay, we have the thing now out of the box, but the impact that it has on us, is that really anything new? We have been trying for, I don't know, 70, 80 years to put critical thinking into our teaching curriculum. And now we see, yeah, you can only benefit from using ChatGPT if you have this gift of critical thinking. So, can we start teaching that? now?
Yeah, exactly. So that's the important thing, you know, when I talk to, for example, people from the government side, then sometimes, or some edtech companies, then sometimes they say, hey, yeah, we just use these systems and everything will be great, right? No, as I try to explain also in the previous answer, before we can benefit and the society can benefit from these systems, we need to actually help children to get to that position that they can use these systems. So absolutely, and this is, I think, has been a thread throughout the talk, or I hoped it would be, that without this general system around it, these systems are not beneficial, or they are beneficial for most of you here who are extremely smart, know how to use technology, etc. But for an average person, they are not useful without these basic things that we need to get right first. So I think that's, in that sense, I'm very grateful for these questions because they helped me to clarify this very important point. Yeah.
Thanks for a great talk. I think it sounds like really great plan, and I very much believe in you being able to carry it forward. I'm wondering about the kind of the quick hacks that can be done. As you pointed out, one problem is that the students are just asking the GPT models to do their homework for them, and then they don't learn themselves. Have you tried already, or kind of do you believe that it can be with a relatively easy prompt to kind of guide the model to not give the answers right away? I mean, when a student asks, or the pupil, school kid asks kind of a grown-up that, please help me do the homework, the grown-up knows that they shouldn't do it for them, because that's not a way to learn. So if you can kind of teach the GPT model to be that grown-up who also knows that the student should go the hard way and try to do things by him or herself, then that would be great. So do you think that can be maybe relatively easily solved?
Yeah, it's a great point, and in fact, it's already, some companies are doing it. I mean, Khan Academy is actually using this kind of a system. What's the name? Khan Amigo something, yeah, something. This is a GPT-4 based tool that is within the Khan Academy. You can solve tasks, and then if you would ask it, right, give me the answer, then it would basically say, no, I will not give you the answer, but I will help you to find the answer yourself. So in that system, within the Khan Academy system, it is used in that sense in the right way. However, the problem is, of course, that the student can say, wait, that's too tough, and open just ChatGPT and ask the question by itself. So in that sense, before we can regulate OpenAI, you know, we can do these tools, and as I said, these tools have been developed already, but the students can get around it still. So we need to kind of bring the knowledge to the students. Yeah.
Hello, I'm Alan Tkaczyk from Institute of Technology, and here in Institute of Computer Science, obviously, we're familiar with computer viruses and antivirus. So my question is have you heard of any research, you know, going on as far as like detecting the text which is generated by GPT-4 or by ChatGPT? So let me give an example. I think one of the problems of like this Pandora's box, as maybe Ulrich has kind of said, is that, you know, this is out there. You know, ChatGPT is free, GPT-4 can be purchased, but should there be some effort to develop like a GPT-5, which would be somehow more restricted, which could somehow detect all text which is generated by the previous ones? Thank you.
Yeah, thank you. Yeah, of course, there are, these tools are being developed, and some companies are, I think, already kind of selling these kinds of tools. However, my latest knowledge is that these tools for detecting are not really sensitive, in the sense that if you would give them a speech by the Estonian president or Shakespearean text, or, you know, the talk by Jaak Vilo, then they might also say that it's generated by GPT. Or was your talk generated by GPT? Anyway, so the point is that they are not sensitive to the level that we could actually apply them in critical decisions, such as deciding whether a thesis has been written partly by this GPT, right? But these tools, of course, are being developed continuously. Yeah.
Last short question.
Thank you. So ATI Academy is about building some capacities in some frontiers. So my question would be sort of from technical perspective. Recent advancement in large language model, natural language processing, machine learning, and transformers definitely came with this wave of technology. But we are, as IT, don't work in isolated Iceland. So what are the enabling and associated technologies that need to be developed to improve, enhance the business impact of such technologies and lead the trend a decade ahead?
Yes, here I will give a short answer because my time is anyway up, that there will be more competent people in this room than me. Perhaps they will even give a talk next, and then you can ask them. So yeah, a man has to know his limits. Thank you very much.
Thank you.
Is it fine? Yeah, so hello everyone. So very timely topic. This is ChatGPT, very well, interesting topic to talk about. But today I'm not talking about GPT because I don't work with ChatGPT. I just work with fundamental problems in pervasive computing. So today I'm here to talk about sensors for daily life. And I think, well, all of you might be aware of what a sensor is. And because, well, we use sensors for everyday applications, even if we are not aware about them. And then today in my talk, I want to talk about a new wearable that we have developed in my team. And this new wearable actually supporting new type of applications from personal safety to actually health. But before talking about this new wearable, let's talk about what sensors are. So a brief history of sensors. Well, sensors are typically used for monitoring and measuring. So from ages ago, we have been interested in measuring things. The first recorded sensors that come to our records is the temperature sensor. So ages ago, Eero of Alexandria, he had a very good knowledge about how liquids, they respond to different temperatures. So then he used this knowledge actually to develop a scale that then he can use for monitoring environmental temperature. Afterwards, of course, many sensors, they were developed, but was not until we have Michael Faraday, which actually he was the one to introduce the magnetometer. So from that, he developed this for, well, measuring the intensity of magnetic fields and as well to detect them. And that was a kind of a breakthrough because, well, electronic devices started. So then we have a lot of different sensors that were developed in parallel, like radar, sonar, and so on. But the next breakthrough came with actually when the sensors were part of our products. They came to the users. So then here you can see the first prototype of one commercial accelerometer, and this commercial accelerometer was used within aircrafts, actually, to measure the stability of the flights. And well, there are many different types of sensors, but I use these three because nowadays you can find these sensors like in a very miniaturized manner inside your smartphones, and they are off the shelf and they are very useful. They provide you with a lot of great user experience so that you can use your applications in a very nice manner. But besides using the sensors in personal devices, well, we have envisioned using sensors not just like in the environment, but in the body as well. So That's how pervasive computing emerged as a scientific domain, because we want to introduce these sensors, deploy them, so that we can measure interesting things. So nowadays, well, from the 80s, we have been investigating about different types of wearables, different types of sensors. Nowadays, we have smartwatches, smart bracelets that they can measure heart rate. We have as well some other type of sensors like smart clothing that they can, detect like how physical activities are performed, whether they are strong or they are like not that high. And then we also have come to the point in which we have sensors that can be tattooed in the human body, so that we can derive from there some sort of things like respiratory rate. Well, now sensors are very small, and you might think like, well, we have sensors for everything, because actually we have sensors for everything. But then, so what are the challenges here? What are the scientific challenges that we have to take care to investigate? Well, to exemplify this, I want to show you here one example of this, this automatic door here. So usually sensors are developed not with a specific application in mind, but then they are just developed for capturing some sensor information. So we can actually use different sensors to support this application. So for instance, we can use a light sensor, so that when the light beam is produced and some people just obstruct the light beam, this intensity of the light is reflected back to the sensor, so we can detect when a person is actually in front of the door. Or we could use actually as well an ultrasonic sensor. So the ultrasonic sensor just produces a sound wave, and this sound wave just bounces back and forth. And if there is something obstructing the way of the sensor, of course it will bounce back faster. And there is other types of sensors as well, that for instance this photoelectric that just produces a continuous beam of information, and when this is obstructed, well, we can actually detect that something is there, and then we can just trigger the opening event. So the purpose here is that we have sensors, but we need to repurpose them, we need to investigate about them, how we can use them. And the problem is that, well, we have small sensors, but miniaturization is far from enough. There's a lot of challenges of using these sensors. So, for instance, all the sensor information captured by these devices, the information is coarse-grained. We cannot use it for performing very critical decisions. So, for instance, in the example of the door, well, it's kind of not critical. It's just open and close. But for instance, if we want to use them for other critical applications, well, the quality of the data provided for those sensors is not that good. So then it's quite volatile. This has a lot of variations. It depends where the sensor is deployed, where it operates, how it's configured, and so on. So for instance, here you can see water quality sensor. So imagine that we have like a set of sensors, and we want to, well, deploy them to measure the pollution that might be going on in Emajogi. So then we could actually attach some Raspberry Pi there and then deploy them. And then, well, we will get information about pollution. For instance, this sensor is about turbidity. We will get that information, but the information that we obtain is not going to be that granular enough to determine, for instance, what was that made the water turbid. If we want that information, actually, we have to deploy more sophisticated sensors. So for instance, you see this base station here, which is quite bulky, expensive, but it's quite accurate, and we can deploy it there. But, well, now we cannot have all the sensors throughout the river. Probably we are going to have just this station, because also this requires some experts to use it. Another example as well is for agricultural purposes, so soil estimation. We can have small sensors to detect different attributes of the soil. But then if we want actually like very precise information about the soil quality, we need to use more sophisticated devices, which are bulky, and you need as well some expertise, like for instance, this spectrometer. So then for dealing with these problems of data, well, applying data science methods to sensor data has been explored for ages. So then, for instance, data science methods can improve the estimations of the sensors. So here you can see two applications that now they are possible after data science is applied, for instance, in the case of wireless signals. So wireless signals now, besides just recognizing people, they actually can tell when a people has, for instance, bad mood, or is happy, or is angry, and so on. Data science methods allow us as well to play with the data so that, for instance, like these chip interfaces from drones, we can repurpose them so that then we can use that information to actually recognize people. So for instance, a drone can be flying just next to the building and then can detect whether people is inside or not. That's a very interesting application that has many potential usage. So in my group, we actually perform pervasive data science, meaning that we use sensors and we apply these methods. And we have developed, well, these are some selected work, some applications that we have developed by using data science methods and sensor data. So for instance, we have some applications that actually can detect whether there is devices, surveillance devices recording you in indoor environments. So for instance, hidden cameras. We have used smart plants as well. So for instance, the smart plants with sensors can detect the amount of people which is in the room. So if we have a smart plant here, we can detect how many people is inside. And we have used as well small sensors augmenting nano drones so that we can produce or estimate fruit quality at high altitudes. Just for instance, if they're hanging in the tree, then the drone can come there and then, well, estimate the quality and to see how it's growing. Well, it's not just about having the data, applying data science methods, because, yeah, it's not just about using machine learning. There is a lot of different problems and a lot of things that we have experienced while developing the research. So one thing that we have learned so far is that the design of the sensor matters a lot when we are collecting information. So besides trying to improve the sensor data with data science methods, we actually need to actually take care on the design, how we are deploying the sensor, how we are integrating it, and how we are embedding this either in the surroundings or in the human body. So we need sensors which are easy to use, because, well, if this is too complicated, no one can use it. Also, we need sensors that they require fast estimations, because if the sensor takes too long to take measurements of something, that provides very poor quality of experience to users. They have to be invisible, because if they are invisible, then it's easier for humans to interact with them. And then, because these sensors, they are small and they are not that accurate, we think that, well, it's not just task of a single sensor to take measurements, but actually we can use different types of sensors to complement each other. So for instance, we can have, or we can think in terms of having a heart rate sensor embedded in the smartwatch, but then we can put as well different other sensors like tattoo in other parts of the body, so that we can have consensus about whether the information that is captured and that is being monitored by these sensors can be then accurate or not. So today, well, to exemplify all of these principles that we have experienced, all of these lessons learned, that what we have found, I want to present you this new smart ring design. So smart rings, you can see here at the top, a classical design, but ours is a little bit different, because classical smart rings, they have the sensors, they internalize the sensor, so that from the skin of the person, we can get then estimations and we can derive some insights. But in our case, what we have done instead is that we have externalized the sensor so that we can collect information about the interactions of the individuals with the objects and with the environment. This new ring can be used in any finger, of course. You can see here positions 1, 2, and 3. But then it provides the best performance according to our results when it's wear in this next to the, close to the little finger. And with this new ring, we have actually created two different applications, well, different applications, but I would present here two. One oriented to health and one oriented to personal safety. The one oriented to health is called Hippo, because we like to put names to our research, so to make it fun. And the one that it's oriented to personal safety is called Hedgehog. So we have put this prototype with, well, simple devices, fast prototyping devices, different technologies. We have tested rigorously in controlled environments. We have presented this demo as well live, not just in scientific events, but also in, broadcasts as well. So live demos that have demonstrated the potential of how to use this ring and why it's valuable to continue improving it further. So let's talk a little bit about HIPPO first. So HIPPO is an application that is developed for actually monitoring hand grip strength. So for instance, probably all of you know this device here. So this device is called dynamometer. And then when you go to a health check, you use this device so that when you provide this information, they can tell, oh, you have hand grip strength, which is weak, normal, or it's strong. And this information typically is provided once per year or each couple of years. But the idea here is that with the smart ring, we can detect these changes in hand grip quickly, continuously, so that we can react when there is these changes, because hand grip strength is a very good indicator, like for instance, determine whether a person is on set of diabetes, muscle loss, and even obesity. So then how HIPPO works? HIPPO works, exploits the principle of light scattering. So this means that when a beam of light is just projected into a surface, there is a pattern. And when this pattern is reflected back, then we can put a fingerprint on this. And then as this surface changes, also the pattern also changes. So for instance, we can actually extrapolate hand grip strength just by looking at the differences between surfaces. So for instance, when a person is just squeezing something, then there is an initial surface and there is a final surface, and from that changes, we can actually derive hand grip strength continuously. Of course, we have tested our smart ring, this application, and we have used golden standard, which is the dynamometer, and we have used other type of specialized pressure sensors because there is pressure sensors, but what we are doing basically is using light to measure pressure. And after all the experiments that we have performed, we can see that, our smart ring actually performs quite well. One interesting finding that we came up with is that the smart ring needs to be configured depending on whether the person that is using it is a male or is a female, because, there is a different grip that these two type of people have. So then as long as the smart ring is configured properly, of course, it's going to work nicely. And the next application is Hedgehog. So Hedgehog is used for detecting dream spiking on wearables. So basically, spiking means that when you're in a social context, someone tries to put some drugs or something in your drink so that later, you are vulnerable and they can take advantage of you. So this is for personal safety. This drink spiking is a huge problem, especially in younger populations. And currently, the only solutions that there are is, some guidelines and principles. So for instance, younger people is told to just keep an eye on your drink, or, just when you buy something, just be sure that it's sealed, it's open in front of you. And then, and then there has been nail polisher as well that change of color and so on. And then utensils like straws also change of color, but they're not reusable. They can be used once, and then you cannot use it anymore. But in our ring, it's scalable for different drugs, different liquids, and so on. So how Hedgehog works? Well, Hedgehog uses the principle of light reflectivity. First of all, to establish a fingerprint of the liquid, and then as compounds are added into the liquid, then this fingerprint is disturbed. So then by looking at the changes, actually we can tell what kind of thing is inside the liquid. And because of the movements of the particles from top to bottom, also we can tell what could be or what is the most likely thing that is inside the drink. So we have tested rigorously. We have tested with different types of drinks, alcoholic drinks, soft drinks, different type of glasses, different types of compounds, and we have demonstrated this as well in practice. We are at the point that we are expanding this further for commercialization because it's a very promising solution. And then so far, the results show to be very promising to be effectively used in the wild. And then, well, with these two applications, I'm demonstrating how the principles of playing with sensors, playing with data science methods, playing with the small low-cost sensors, and then taking care of all the design, enable us to actually develop this kind of new, sophisticated, and useful applications. So in summary, miniaturized sensors can support different applications, but they are, well, far from enough. There's a lot of accuracy issues, and they're not going anywhere soon. And then we can use data science to improve sensor estimations, but thinking or rethinking the design is very important. And here I have shown you two applications, one hedgehog and one hippo. And I want to thank as well to the IoT Academy program, because this was developed during the IoT Academy. So then, yeah, these ideas came up. All the researchers that are working, actually this is the topic of one of my PhD students. And then, yeah, we have spent a lot of time, and it has been fun playing with all of these sensors and trying new things. Yeah, thank you.
Okay, thanks, Huber, for this talk, because it relates to a lot of what my work is doing too. So like me, you're working a lot with hardware and design, and also with engineering. And so I wonder, what's your experience with the students coming out of our program? How well do they fit in this type of research? Are we doing the wrong type of research, or are we creating the wrong type of students?
Yes, I think I get your point. And then, for instance, playing with, let's say, software and data, it's not that challenging, at least, you know, like for other disciplines. But at least in the case of pervasive computing, IoT, and so on, yeah, people require actually to use more or some knowledge in hardware. And this has been a challenge because, well, the amount of people that is into hardware or playing with hardware, of course, it's quite kind of a few. But of course, all of these frameworks, all of these methods, you know, Arduino, Raspberry Pi, they provide tools, excellent tools, so that this can be learned very fast. So then I think recruiting people has been more about showing, you know, what cool stuff we can do. And then how this cool stuff then can be applied, can be commercialized, and can be used for, you know, like doing something new. Yeah, of course.
He can be approached afternoon or later. So let's move on to the next, Raivo.
Hello, my name is Raivo Kolde. I'm a IT Academy Associate Professor in Health Informatics, and I'm going to tell you a little bit about like what our group is doing in here. And to start, I just wanted to show a little example of a recent study that we just performed. And like many health researchers, like we are also interested in COVID and what happens to the people after COVID, so-called like long COVID. And we figured that like nice thing to study would be actually the drugs that people are taking, because like maybe not all the ailments that they have are not properly encoded in the health data that we can access. But like if person has a serious problem, they are usually getting drug for that. And like looking drugs is a good proxy for all kinds of health problems that they have. And for this, we used a sample of roughly 130K Estonians. And we used this clever methodology that we used the patient itself as its control to see like what drugs is he taking more after COVID compared to before COVID. And as a result, we identified a number of drugs that were more commonly prescribed to the patients after COVID than before COVID. And there were like diabetes drugs, heart drugs, and sedatives and so on. So we got some interesting results, and the results are submitted and soon published. But not these results are the ones that I want to tell you about today. It's more that what it takes to do this kind of research anywhere, but also here in Estonia. So to carry out this type of research, it doesn't only help that we are cool guys with great ideas, we also need data, we need the methodological expertise to design a right study, but also technical expertise to actually code it up, but also we need clinical expertise. So in this case, we had the data for more than 100,000 Estonians. We had the technical expertise, and also we consulted extensively with different clinicians who were actually treating the patients with COVID. So all of these are necessary aspects to make these types of studies come together, and you cannot like just have one of these. And when I came back to Estonia and started this group with the help of IT Academy now 4 years ago, then I pretty much only had this this part, the methodological and technical expertise, but I didn't have any the others. And I figured that the first thing that we should do is, in Estonia we have actually pretty nice health data, so we started working on the health data. And since I cannot go and study to be a doctor, I don't have time for that, then we have to find also collaborators with the clinical expertise. But like surprisingly, for me at least, much of the work thus far has gone into the data, and that's why I'm going to tell a little bit more about the data part of this. So what does good data look like? So this is an example of the discharge report from Estonian Digilugu, which is a pretty nice database collecting all the interactions from between patients and medical service providers, and and there is a lot of information in there. And first, good data should be rich. It should capture many features of the process of treating people. It should be complete, that like most of the things that are done to the patients should be also end up in the database, and it should be representative, so that actually when we are trying to study a problem, we are looking at it in a representative sample that actually gives an accurate idea like of the people that we are trying to study. And I think these things are more or less covered by Estonian health data as it is right now. So it has many features, it's relatively complete, and it's also representative because it covers all the different health service providers and also all the patients. So that's nice. But also for research, the data should be like ready for analysis. It's great if the data is structured, it's clean that the values are actually what they are supposed to be, and it should be available. And that's already a problem with Estonian health data, because if you know anything about how Digilugu is structured, this thing is basically an XML document, and the whole Estonian medical database is a collection of these XML documents, and these are not very easy to process. And also the data is not clean. If you start looking at the individual values in the data, you can find all kinds of curiosities in there, and like sometimes you think that, is there even possible something to do with the data? But usually there is. And also, the data is not very well available, because getting the data out of the Digilugu is often a very time-consuming process. So all of these were the challenges that we had to overcome when starting these types of research. But I add another point about like what the good data should look like. It's also the data should be standardized, because even if we have this nice data for Estonia, we build a cool study about that. When we want to go do the study somewhere else, so here it's visualized as this iron that we can plug into Estonian data, but if we want to plug the same study somewhere else, it turns out it doesn't work because the data elsewhere looks different. And we are stuck with a small Estonian data set that we have. And for this, we go one step further, and we have been extensively thinking about the standardization of the health data. And we are not coming up with the standards ourselves, but we have adopted this OMOP common data model that is meant for these types of applications, the research applications, that can hold basically any type of health data. But what it provides is provides a data structure that is very well structured. For each piece of medical information about the patient, in which table it should go and how should it be coded in there. And if the data is put into this format, and we are developing a study based on this format, then we can apply it on our own data, but we can apply it on also a host of other data sets. But of course, getting the data into this type of format might not always be easy. So what we have been working about is getting the source data, the raw data, into this format. And this is called the ETL process, shorthand for extract, transform, and load, which is that like first we extract the data from different sources in Estonia, the health insurance claims, the digital prescriptions, and the Digilugu EHR documents. Each one of these sources itself is incomplete for research in a sense that, like, for example, health insurance claims is very good for diagnosis codes, but it doesn't have any measurement information in there. It has only information about what measurements were made, but not what the measurement values were. The Digilugu documents are good because there you can actually get the measurement values. And digital prescription is a very good database just because you get all the prescriptions in one place. So it's also a great source of information. So what we are doing is we have procedures to link it all together, to clean the data, so we can get much more out of that data. And then we have also spent quite a bit of time to code all this information into this standard format so we can load it into the OMOP common data model. And once it's standardized, then we can use all kinds of different already available tools to check the quality and go back if necessary and do this process in cycles that we can get really a good data set for research. And we have been applying, and yeah, if you want to learn more, then we just have put out a preprint that we also submitted as a publication about the whole process that we have done in here. And we have used this process not only on one data set, but as in Estonia, it's very hard to get like all the data together into one place. But what you can do is that you can ask data for different studies. So we have asked the data for different studies and then use the same procedure to convert this data. For example, we have 10% of Estonian population, their discharge reports, insurance claims, and e-prescriptions. Then we have the Estonian Biobank donor health data. Again, the same data points, but also information from different registries. And also we have quite a lot of COVID cases and batch controls for whom we also have like mainly the insurance data. And actually we have more data sets. And based on these data sets, once we have processed them to have really high quality, then we have used these data sets to study, for example, drug utilization, cancer risk factors, healthcare utilization, and so on. And I think this brings out a different aspect, is that like this process of transforming the data is not like one-off thing that we take the code and apply it to the data. It's actually a process with a feedback loop, because with each of these studies, we learn something new with the data. So collaborating with clinicians, we actually learn like how the patients are treated, how the things are coded in the data, and like what would be appropriate way of looking at the data. So we can collect all this information, put it into our pipeline, and run it again in all our data sets, and in all the subsequent studies we can already use this improved version of the data. And this is a process that keeps getting better all the time. So this is something that we have done. We have now pretty good data that is getting better, and we are applying for more data for different studies. But this data is now driving the research that we do. So since we have good Estonian data, it's enabling studies on the Estonian data, so, and allowing us to ask novel questions. For example, we had taken out from Digilogo the different types of human papilloma virus test results. And like when we showed it to the doctors we were working with, they were surprised that we have so much data about that in one place. And they had an idea that we should just do the study at like, what is the prevalence of different human papilloma virus types in Estonia? Because this is a very important information. This is the major risk factor for cervical cancer. And if we don't know, and like different types have different carcinogenicity, so if we don't know like which types are present in Estonia, it's also harder to create these different prevention measures and prevention interventions that are done for cervical cancer. So, but like having this data in one place, extracted from the Digilogo, actually gave us the opportunity to study this on large scale. At the same time, we learned a lot by doing this study, and we are using the data that we extracted from this for this study also in the next studies, where we are looking how the cervical cancers are treated in Estonia and how they are prevented, and how does this treatment follow the treatment guidelines. So this was the study in Estonia, but at the same time, since we have standardized the data, we can also do the study, do studies that are across the different countries, and we have participated in quite many studies. Here I put just some examples. For example, we were part of a big consortium that was studying background incidence rates for adverse events of special interest for COVID-19. So this study actually included more than 26 databases, and there were more than 24 million COVID cases across all the databases. And this shows you what kind of scale you can achieve if you standardize your data and pool it together over the borders. And then there was this other asthma drug utilization across 6 countries now, and here you can see some results of it as well. So these were the new patients, and like we were just looking like what drugs are prescribed to them and then in which order. And this one in the bottom here is Estonia, and you can see that, for example, in Estonia, the drugs that are prescribed to the patients are very different to the ones prescribed in US or in UK or in Netherlands. So this is again like interesting information that has to be taken into account if you are comparing the outcomes of asthma treatment in different countries. But both of these were like one-off studies where somebody took together like different data sets, data partners that were interested, and like ran a study on this. But this can be actually formalized and industrialized, because the need for evidence is there in many places. And one institution that needs a lot of evidence to do their research is European Medicines Agency, because they are responsible of approving drugs in Europe and regulating how the drugs are used across Europe. And we all would actually like that their decisions would be more evidence-based, and they would use the most appropriate evidence in each time. But actually getting this evidence is really hard. And EMA has used these ideas like presented before, like standardizing the data and putting together like these huge studies to create this Darwin research network with this, which is illustrated in here. So this is EMA that has these different subcommittees that need evidence, and they are interacting with this Darwin Coordination Center that is creating the studies based on the questions that EMA has and sending it out to the data partners and like getting the information back. And since all the data is pre-processed already and like standardized, then these studies can be done in very quick order. So simpler studies should take weeks, and more complex ones should take months. So this network was launched in last year We are part of that using Estonian Biobank data, and currently we are in process of running 2 studies, but in next years the numbers should increase exponentially, like to tens of studies in a year. And I think it's a good example how by solving these technical problems in data, we can actually have impact on the everyday lives of the people in terms of like how the medicines are regulated and approved. And finally, when we create these huge networks of, for research, it also creates new problems to solve. And this is the place where we can use now our methodological knowledge that we can start building new research methods that can be used in these huge network studies. For example, one idea that we are currently pursuing is that like we have created this package for learning Markov models for modeling health trajectories on top of these databases. And these Markov models are usually used in health economic evaluations of different medications. And what is done usually is that like these models are based on literature. The parameters are taken one from like one study, one from the other study, and these might not reflect what's actually happening in Estonia or what's happening in Netherlands. As you saw, for example, asthma is treated totally different like in Estonia and in Netherlands and in US. And if you use the model from US to model the drug effectiveness or like the drug cost effectiveness in Estonia, then you might get like very skewed results, especially the healthcare costs, and the cost structure is also different between different countries. But by doing this on a network scale, we can have these common definitions for the models between the countries and actually get the results on the local data. And this is something that we are working on, and we also try to tap into the network ourselves. So we have designed a study that we are trying to run now on these different data partners and see how well do the results match across different countries. So it shows you the opportunities that we get, that we have our own data in the standard format, but like we have also access to now to these other data partners that have the data in the same format, and we can use it in our research as well. So that's pretty much it that I wanted to tell you today, is that we have the process for cleaning and linking Estonian health data sources. So it's continuously improving, and like it's applied to multiple data sets. And data drives really the clinical research and the collaborations. So I cannot become a doctor myself, but we have lots of doctors to work with thanks to having a great data set. So through Estonian clinical studies, but also participation in research networks. And now for the students joining the group, there are many opportunities for the method and tool development. We have already several under development, and we have also started a first network study, like really utilizing the power of Estonian data, but also the data sources around the world. And this work is not done only by me, but there is a larger group of people. You can see some of these people in here, maybe not all. And if you want to learn more about that, you can look at our website, healthinformaticscs.ut.ee, and of course go to the poster session. We have several posters up, and we are happy to talk to you if you have any ideas or questions. Yeah, thank you.
Thank you for the talk. So I would like to ask about this first point in your summary, this processes for cleaning up the data. You also had the slide. It looks quite complicated. So I'm curious, what are the correctness and testing challenges, so to say. So how do you ensure that your transformations on the data cleanup, that there is no mistakes in your tools? How do you verify what formal methods do you apply, and such things. So, any comments on correctness?
So we certainly have some tests in various points of our pipeline, but like often it is also just like by actually doing the studies alongside that you see the problems coming up in really unexpected places, and like you're learning with every study like what actually can be done. So that's why I'm very that's why I don't think that it would be good if like this task would be left to the government or like governmental agencies that are providing us data and use it as it is, because we learn that like every time there will be some problem with the data that might be easy to fix, but if it's if we don't have control over that process, it's just that like we would fail like most of the studies that we embark on. So
yeah, thanks for the nice presentation. I just was hearing your talk about the amount of data that you have available and that you are pre-processing, and it's very impressive, the amount of data that you have collected from different networks. But then my question was regarding more of applying these, you know, like standard methods for curation, preparation, and transformation. Have you have any experiences of, or can you tell like how scalable are those methods when you apply them on the data, or have you been with the need of changing them so that they will, you know, analyze the data faster, or something?
So right now, like if you take like all the documents from Estonian Digilugu database, then just processing these will take like, not all the documents, but like all documents for like, for example, 200,000 Estonian biobank participants, then it barely runs through. So, but like if you would get, for example, like, I don't know, 3 times more data, then we would have to start like thinking about like optimizing the processes. But like right now it has been kind of okay with the big virtual server that like you can do it on one server, but like at some point we can see that there are software development challenges also in there that need to be taken account of.
Usually health touches everybody. How come you do Was there some more questions?
Yeah. Yeah.
Thank you for the talk. A question related to the type of data that you're processing in your transformation. The question is that this ELF data, in many cases, well, there is Estonian system is a good example that there is a lot of information which is sort of predetermined. So the result, success or fail or whatever, those are easy information. But now if you stumble upon freely written text, so what about this? Are you extracting data from there?
Yes.
Or this is,
yes, this is like when I showed you the document, there are like different parts of the document. So some of those are structured and some of those are free text. Even the structured parts can be pretty hard to parse if you want to get the data out really clean. But we have pipeline for that, but we have also pipelines for free text processing. So we are certainly extracting some of the measurements from there. And for example, the human papillomavirus types were also in the free text. So we had to get them out from there. And
okay, sorry, can I interrupt?
Yes.
If you just pick keywords, that's one thing. But getting context out of, for example, a final outcome of a case in treatment. So if a human reads it, it has some really, probably some really expert opinions in there. Are you going into that direction as well to get information from there? Or?
Certainly we are exploring things, and like we are exploring the all these large language models also in terms of that. So like you can come to our poster to see like what we are trying to do in there. But certainly, just to extract things, maybe keywords are often not enough because like keywords can be ambiguous. But like if these large language models also allow you to take the context into account, so you can get much more accurate representations of things. So we are certainly exploring that, but we don't have too much in practice.
Yes, hello. I think it's a very interesting presentation. So my name is Antti Animo. I work here only part-time. And so elsewhere I work in kind of artificial intelligence from the perspective of getting companies to utilize it somehow meaningfully in a way that would not be harmful to civil society and so forth, citizens. And one of the problems when working with companies is that they are awfully jealous of the data sets. And then it sometimes also goes for all kinds of public data sets. How do you deal with the fact that these kind of original owners of these data sets, which you make compatible with one another, how do you deal with the kind of the politics and the tensions between different providers of data?
So that's an issue that, like, fortunately in Estonia, the data that we are using is all from national sources. We have the one national health insurer, we have one national EHR database, so we can take a lot of data from there. But of course, we just cannot tell that, like, give us all your data, or like we would like to do that, but like I'm not sure if they are really happy about that. So we are using the legal means that, like, allow scientific research, and then we are trying to get big enough data sets that actually can tell us something meaningful. But of course, we would like to have actually the whole Estonian data set available, because Estonia is so small. So when you go to these different, like, network studies and, like, talk with other people and tell that, like, we have this great data set of like 200,000 people, then they say, oh, we have like 5.2 million. So, and if this 200,000 becomes really small when you start looking at the particular diseases, because like in Estonia, all diseases are basically rare diseases. You have like few hundred patients. So if we don't take COVID, then all the other diseases are pretty rare. So yeah. Thank you.
Okay, hello. My name is Paršovs, and I'm the lead of the Applied Cybersecurity Research Group here in the University of Tartu. And in this presentation, I will briefly introduce our group and also try to give you quite a wide overview of the topics that we have worked on over these last 4 years of the IT academia funding. So let's start with the mission and vision. So in one sentence, what do we do is that we perform highly practical research in the field of cybersecurity, evaluating the security of the technology solutions used in our everyday life. And the emphasis here is on practical cybersecurity research, because we are doing applied research and we are not much into theory and fundamental research as maybe other research groups here in the University of Tartu are involved. So also our focus is especially directed towards solutions with significant public interest that are used in Estonia. And in practice, this covers topics such as electronic identity, Estonian ID card, mobile ID, digital signatures, internet voting, and similar topics. And our greater aim is to develop our competence to act as an independent authority, evaluating the security assurance of technologies, products, and services provided by government, industry, and other institutions. And here again, the stress is on independence, because we kind of want to maintain this research freedom to be able to freely pick the objects and subjects of our study, and to not be influenced by, let's say, by the business interests of the party who provides funding. And here, the IT academia funding has been very successful, and also other sources of funding, so to enable us to maintain this independence so far, about which we are very happy. And also know that the security, the word security here is in a very broad sense. So we are interested in all aspects of cybersecurity, from hardware security, vulnerabilities in the source code, up to the analysis of the security architecture of the solution. So our ambition here is very, very high. And we serve the public by making our research publicly available and sharing our knowledge through various teaching activities. Now, making research publicly available is kind of may seem obvious, but actually in the field of cybersecurity, this is not always the case. There is a research that is done in secrecy and avoiding discussing security issues in public. But so our belief is that actually security research has to be made public, because otherwise it's hard to learn from the mistakes to improve the situation and then build a more secure solutions. And this is also the reason that we try to avoid non-disclosure agreements. So we are open to collaboration with industry, but if the solution is used by a significant part of society, then it's actually in the interest of society that these research findings are made publicly available. And so the main form of how we collaborate with the industry is that we collaborate by reporting our findings under a responsible vulnerability disclosure process. And so what it means in practice is that we usually contact the responsible party and give some time this party to act on our findings, let it be fixing the vulnerability or in any other way, and only then we publish our findings. And this process so far has worked very well. Now, so we are 3 people full-time employed in the University of Tartu. This is me. This is Danielle Morgan in junior researcher fellow position. She's also a PhD student currently. And Denis Lapkapizis in junior lecturer position. So a very important part of our work is teaching. And so our group is responsible for teaching 3 courses. The first course is Applied Cryptography course, which is taught by me and Denis Lapkapizis. This course covers the most popular topics in real-world cryptography. And what is unique about this course is that these topics are explained without delving into the formal definitions and math. So these courses were used for those IT engineers who want to use or apply real-world cryptography, but who are maybe not interested in the math behind the cryptography. The second course which we are teaching is Wireless Technologies and Security. This course is taught by Danielle Morgan, and this course covers the most popular wireless technologies, Wi-Fi, NFC, GSM, GPS, and also basic radio communication. And what is cool about this course is that this is a hands-on course because each student is being given a set of hardware which they have to use to implement homework. This is an NFC reader, NFC cards, HackerF1 software-defined radio hardware to send and receive basic signals, a Wi-Fi adapter for implementing Wi-Fi attacks, and a very basic wireless doorbell. And this is used to try to capture this radio signal and then try to replay it. And the third course which we are teaching is Web Application Security, taught by Denis Kapizis. And this course then covers the most popular web application vulnerabilities, and such as SQL injection, cross-site request forgery, and similar. So this is a new course, only 3 credit point course. Still, the material in this course needs to be improved. So these are the 3 courses which we are teaching. We're also supervising bachelor's and master's students, about which I will tell in the next couple of slides. So what we also have is a quite unique, let's say, collection of equipment which can be used for security analysis. So this is mostly hardware for hardware security analysis and for working with wireless signals. You can see the whole database in our website. Now, okay, so this was kind of a very brief introduction in our research group. In the rest of this presentation, I will go over various topics on which we and our students have worked over these last 4 years of the IT Academy funding. And I will not go into the details. I'll be very brief. I will jump from topic to topic, but I hope that you'll be able to keep up with the pace and also that you'll find this compilation interesting. So the first topic which I cannot not mention is the Estonian ID card. This is the topic I have researched for many years, also before I joined the University of Tartu. But the main findings were summarized in my PhD thesis, which I completed in 2021. I will not talk about this because, yeah, there's, for instance, this B-side Stalin conference presentation, which very well gives the overview. And I just mentioned 2 related articles which were completed in the IT Academy funding period. The first very important article is this Usenix paper, which covered the security flaws found in the key management of the ID card. The long story short, based on our analysis, the Estonian state learned that the ID card manufacturer had generated private keys outside the card, breaching the security requirements of the contract, and the Estonian state then went to the court asking for damages. Now, another topic which I have focused significantly on is on the Estonian ID crisis in 2017. I think all of you remember this vulnerability in the ID card chip where it turned out that the chip generates weak keys, which can be factorized or cracked, right? And which led to that crisis. So in this paper, I looked at the legal issues. Basically, I looked how precisely the state was able to follow the legal requirements while solving this crisis and what are the related lessons that can be learned. What is perhaps less known is this work by our master student, Bruno Produit, where he actually managed to optimize this rock attack, the attack which was behind this 2017 ID card crisis. So what he did first is that he provided implementation of the attack, which can be run in parallel, for instance, on HPC. And he also found that by analyzing the real ID card keys, the attack can be performed much faster. So the initial estimate was that it is required 140 CPU years to factorize the key, but he found that on average, actually, it's doable in 35 CPU years, which is quite a significant improvement. And here we can see his attack script in action. Another event, ID card-related event, which is important to mention, is that in 2021, the Estonian authorities decided to declassify information about the ID card pin bypass flaw, which was discovered in 2011. So in 2011, a flaw was discovered, was quietly fixed, and then 10 years after the fact, the authorities decided to declassify this information and make these technical details public. So here, my contribution was an independent verification of these technical details and analysis. And this is actually a very good sign, what we observe here, that still, even though 10 years passed, the authorities decided that this information should be made public to the society. And I very much hope that this principle of transparency will be also upheld in the future. Then in 2020, our bachelor student, Semyon Kramchenko, did some set of experiments, and he found that 5 e-services in Estonia are vulnerable to ID card authentication bypass flaw. What it means in practice is that these services didn't correctly implement the ID card certificate check, which basically meant that it's possible to create a fake certificate and impersonate any Estonian ID card user in these services. So this was a very serious flaw, in our opinion. I've informed these companies behind these services. But to our surprise, it turned out that not all companies considered it a serious flaw, because 2 companies from here, for them, it took several months actually to fix the flaw, and then we could go public with these findings. Then in 2021, a flaw was reported in ID card browser extension. So on the left, you see RIA's press release that RIA fixes critical flaw in ID card browser extensions. And on the right, you can see the demonstration video. So in essence, this was a man-in-the-middle attack, meaning that you authenticate with your ID card to some website, but in reality, the owner of that website authenticates on behalf of you to some other e-service or website that uses ID card authentication, in this case, st.e. And what's interesting is that this flaw was due to undocumented feature in browser extension. So the simple fix was to simply remove this undocumented feature from all the computers used in Estonia. But surprisingly, it turned out that Swedbank somehow had found this undocumented feature and had used it in their online bank environment. So it actually required a bit more time until they migrated their production system to different feature, and so that this feature, dangerous feature, could be removed from the browser extension. Now, we have also worked on ID card and NFC communication. Probably you know that the latest generation of Estonian ID cards have NFC interface. So here you can see the antenna connected to the ID card chip. However, the point is that in order to use this wireless NFC connection, you need to use these 6 digits on the bottom of the, I hope you see under the picture. You need to use this 6-digit number as a password to establish a non-trivial cryptographic protocol with the chip and then send these smart card commands over this channel. And here our student Sander Karl Kivivaara, a bachelor student, in his bachelor thesis did a very good work. So what he did was that he documented step by step how this channel can be established, what are the configuration parameters, and he also provided a source code Python samples of how to do it. So this is very good work and very useful for software engineers who wish to implement ID card, NFC communication with the ID card. Then in 2021, some work has been done on WebID. WebID, if you haven't heard, probably you haven't, this is a new software architecture for using ID card to authenticate to websites. This is how it looks from the user's perspective. Maybe it doesn't look too different, but the changes behind the scenes are very significant. So the entire logic and protocol has been moved from TLS protocol, which is blended in the browsers, to the browser extension. And so here we work on the analysis of this solution, also provided some ideas, proposals, how to improve the protocol, and we are very happy that actually RIA implemented these proposed proposals in the final version of the solution. Then some work has been also done on the secure analysis of RIA's authentication service, Tara. So this is how it looks. I think most of you have seen this when trying to authenticate to e-services provided by the government. And while this maybe looks simple, there is actually some non-trivial protocol running behind the scenes where at least 3 parties are involved. Nothing groundbreaking was found. Still some things that can be improved was found and listed in the report. Then the last major ID card related topic which I have worked on is about security improvements for the Estonian ID card. So here in the report I proposed 7 very specific proposals that could be implemented to make the ID card more secure, in my opinion. And this work was done based on the request of the Estonian Police and Border Guard Board, because the new ID card manufacturing contract procurement was ongoing, and they looked for the ideas, proposals. What should we change on the ID card or in its manufacturing process? So we'll see what of this will get implemented. Now, the digital signatures is also something that we have studied. For instance, here, this is the article which we wrote together with lawyer Tonu Mets on the time of signing in the Estonian digital signature scheme. So the main focus in this article was to highlight a very common misconception, that people believe that digital signature provides a cryptographic proof of when exactly the document was signed, which is not true, because here you can see that there is some document which is signed by the President of Estonia on May 2018, and then there is a modified digital signature container which turns out to be signed a year later in October 2019. So this timestamp is actually not the time when the document has been signed. And this then creates a couple of legal implications which were then discussed and analyzed in this article. Now, the related topic on digital signatures was the study of legally invalid digital signatures. So what it means is that it is possible to craft a digital signature which will be reported by the software as being valid, while actually if you go to the court, it is possible to prove that this signature is not legally valid because it was created after the user's certificate was revoked. And so basically the verification algorithm is missing a very important security check which verifies this aspect. And eventually we managed to get this check into the algorithm used by Estonian software, so the latest version should report that indeed signature is not valid. However, we also found out that the same issue is actually widespread over the whole European Union. And it also turned out that the digital signature validation software that is provided by European Council also has this issue, because as you see here it says that the signature is valid, totally passed. So we contacted the developers of this library, but they refused to fix this issue. And their excuse was that this check is not listed in the draft standard of digital signature verification. And indeed, here you can see the ETSI standardization process of that standard at that time. And indeed, this check wasn't listed there. Now, the good thing is that RIA are the members of this standardization team of this standard. And eventually, we managed to get in this check in the final version of the standard, which is very nice. And I hope that the libraries now will be fixed accordingly. Now, mobility is also the topic which we have briefly worked on. So here is the work by our bachelor student, Semyon Krafchenko, where he studied the protocol, or reverse engineering of the protocol, of how SIM card communicates with the mobile phone in order to implement this mobility functionality, pop-ups, pin entry, and signatures. And this is, you can see his experimental setup, which can be used to sniff and modify commands that are exchanged between the SIM card, which is actually that blue thing there, and the mobile phone. And he managed to successfully recover this protocol. The other topic was the work on the mobile document decryption feature. So probably you know that today it is possible to encrypt and decrypt documents using the ID card. However, this functionality is not available for mobile ID users. And here, the company Best Solutions Estonia came up with a pretty smart solution how it could be done using mobile ID. And so our task here was to evaluate this proposal and provide some recommendations. And again, I'm very happy to know that at least in the prototype, this company has implemented the security recommendations that we pointed out in our report, which is not always the case, because there is still a widespread idea that unless the solution is not completely broken, there is no need to improve it or fix even theoretical issues. Smart ID is also the topic which we have looked at. For instance, here a bachelor student, Silver Mala, made a proof of concept malware for Smart ID Android application. So what this malware does is that basically it sniffs the pin codes that are entered by the user, and then later when the Smart ID pop-up comes up, it automatically submits this pin code, the previously captured pin code, by spoofing the touch button clicks. Now, the important point here is that this malware works only if it has root access to the phone. And the thing is that, fully patched, up-to-date phone shouldn't have root access that could be gained by the malware. And then the master student, Edward Ilchuk, proposed how the Smart ID solution could be improved to use ETCDA-based cryptography. So currently it uses RSA-based threshold cryptography scheme, and here he looked how it could be switched to ECDSA to gain a better performance. And he also created a Java implementation of his prototype. Now, the last thing which I want to very briefly mention is the security issues we found in the Tartu smart bike share system. So this topic actually has been more popular amongst our students. Over the years, we have had 3 students who have worked on this and have found quite interesting findings. So the first work was by Abbasi Amefon Afian, who looked at the NFC unlock mechanism used by the Tartu bike share system. And so there is this NFC card, which is used to authorize users. And what she found that the bikes, in practice, do not use all the security features provided by NFC technology, which means that it was trivial to clone the card just by knowing the card number that is printed on the bottom of the card. So we had a meeting in the Tartu City Council where we explained the issue, but then later, when we checked a few months later, it's reported that key not recognized, meaning that this flaw has been fixed. The second work was by Sim Alexander Kut, our bachelor student, who was analyzing Android application of the Tartu Smart Bike Share system. And what he found in his work was that there was one API endpoint where unauthorized import, which in real time reported the actual status information about any bike in the system. So what you see here is the current geolocation when it was unlocked, and also what NFC card was used to unlock the bike. And this was basically a security privacy issue. And here you can see how he tracked himself by querying this API endpoint. And the last work was by Peter Vahe, a bachelor's student, who looked or analyzed how hard or easy it is to make a perfect clone of the NFC card used to unlock the bikes. And he found that, unfortunately, the current technology exists for making a perfect clone of the NFC bus card. Here you can see the Chinese card that can be used for this purpose. And what he also found was a quite interesting race condition that is actually in practice, it is possible to unlock 2 bikes with 1 account, but these bikes have to be unlocked in 5-second interval apart from each other. One bike is unlocked with with NFC card, another one with the application. We reported also this flaw, but as far as I understand, the Tartu City Council didn't consider this to be a serious vulnerability which have to be fixed, which is probably the case. Now, the last thing before completing this presentation, I just want to mention this master thesis by Burak Kankus, on which the ID card face match demo installation is based on. So what you see here is the installation, which you also see outside there, where in the poster session, and this was the first version developed by Burak Kankas, and this is the improved version, which you will see on the second floor. And if you're brave enough, you're welcome to try it out, insert your ID card, and more information about this solution is provided next to it on the poster. So with this, I conclude my presentation. Thank you for attention. And also on this homepage, you can find links to all the information that was actually covered in the previous slide of the presentation. Thank you.
Very interesting. Just wanted to ask, there is a new development in Estonia called Estonian IT security standard.
has that been something, or is it on your scope of vision or of interest? Because I think for the public interest, it holds actually a lot of complexity and might be an interesting topic to look into.
Indeed, it is an interesting topic and a very important topic. And actually, we in the University of Tartu, we have researcher Mari Seba, who is focusing on specifically this security standard. And yeah, we hope that we will have also students and other people looking into it. But our research group is currently not looking into this topic.
Also, the technical and organizational security measures have a massive gap between them, right? There's a totally different abstraction level in the analysis.
Can you comment on the Canadian company going bankrupt at the moment? Did you cause that?
I have to say that they're very outdated. I don't know who went bankrupt. Who went bankrupt?
No, this Tartu city bike producer that
okay.
is on this process.
I see.
These news that it may be shut down.
So yeah, indeed, the technical detail is that this Tartu bike share system is actually provided not by Tartu City Council, but by a Canadian company, which holds actually the system as a closed source system. So it's very hard was for the Tartu City Council to directly patch the flaws that were found. Everything we had to went through this company. Okay, yeah, I heard about this company having some issues, but yeah, I don't think this was the issue. Unfortunately, because hopefully the security should be an aspect that should be evaluated when evaluated in the trust of the company.
It seems to me that there are no further questions and everybody's eager to go for coffee break. Is that the case? Do I get some noise from you? Is that the case? Is that the case? Thank you, Arnis.
Thank
and
you.
Everybody else.
Yeah. Thank you.